Welcome again, Melissa. It's an absolute delight to have you today. So let me briefly introduce Melissa Dell. She is a professor of economics at Harvard University. She works on development economics, political economy, and economic history. And as we will see today, she's also pushing the frontier in terms of making large-scale document digitization available to the masses. And Melissa has published lots of exciting work. My personal favorite is the mining meter in Peru, a paper she published about a decade ago. It also introduced methodological advances, two-dimensional regression discontinuity designs. And today we are hearing about parsing of tables and making them machine readable and usable for research. So Melissa, the floor is yours. You have 1 hour in total, and let's go ahead. Thank you for coming.
Yeah, thank you so much for the invitation and for the introduction. And so today I'm going to be talking about how deep learning can be used to curate data at scale. And so, the motivation for this, people ask me, well, why are you doing this deep learning stuff? Aren't you an economist? But I think really central to anything that we want to study as quantitative social scientists, we need data, obviously. And the data that we have shapes which questions are feasible to answer, but it also shapes the questions that we think to ask in the first place. We're not going to, really think to pose a question for which we would imagine the data couldn't be available. And as a relatively young field, empirical social science and economics, more specifically, has barely begun to scratch the surface in terms of being able to answer questions that are most important to people's lives and to the functioning of society. Essentially, there's a huge number of questions out there that we still have to tackle. And in particular, advances in deep learning applied to challenging problems in computer vision and natural language processing have already revolutionized many fields. You see this in medicine, you see, landing a rover in a difficult terrain on Mars, kind of all sorts of things. And they have a huge potential, I think, in economics as well, for a similar set of tasks, which is to take raw information that is not itself computable and transform that raw information into something that we can actually use in our analyses. But understanding and applying these methods requires significant startup costs. It takes a lot of time, at least it did for me, but it's really remarkable what they can achieve. And I want to talk about some of the resources that my group has been working on to make these methods more accessible to economists. And so just to give a little bit of background, if you go back to the 1990s, economics is a very different field than it is today. And the massive growth of personal computing at that time just completely revolutionized the questions that economists ask and that were feasible to answer. And I think the same thing is true today. As was true 25 years ago, there's been recent monumental advances in computing that have revolutionized a lot of different disciplines and have the potential to significantly expand the questions that we can ask. And in particular, advances in GPU compute and the availability of cheap cloud compute makes it possible to process data at a scale that would have been previously unimaginable. So for the past 3 months, I've been running 1,000 virtual CPUs on Microsoft Azure, right? I obviously would have never had 1,000, CPUs in my home office. And so just with with that compute, you can do so much stuff that just wouldn't have even been thinkable a decade ago. Okay. And so in particular, I want to emphasize, the potential for deep learning methods to transform how we can use raw data in the social science. So raw data takes a lot of different forms. And so a typical one that many of you may be familiar with is scans of different types of documents. It could be statistical tables, it could be government administrative records, firm level reports, newspapers, directories. These scans may be of poor quality, either because of the scanner itself or because the document was not in good shape. And the layouts of these documents can be very highly complex. But this isn't the only, sort of form raw information could take. It could be contained in text, which itself is not a computable object, and you might want to know what's discussed in that text, how it's discussed, what the sentiment is. It could be in photographs and video and audio files and satellite imagery. And while these might seem like very different types of raw information, actually the methods that are used to process them are quite similar, and they're becoming more and more similar, really, with each new paper that's written. These fields have really converged. And so essentially there's, a set of core tools that are very useful for processing these very diverse types of information. And so firstly, deep learning has the potential to unlock, traditional types of data that we're used to using, like statistical tables, but doing so on a large scale in contexts where manual digitization is just completely infeasible. And I think it's also going to change the types of information that can be converted into computable data. As I mentioned, for example, with text, you have to have something in a computable format before you can do an empirical analysis of it. Same thing, historians talk about images that appeared in media and how important those were to public perception. And beforehand, that would have been a data source that's not really computable to us. You're not going to read like 100 million scans of newspapers to pick out images, but that's something that's very straightforward to do with deep learning based methods. Another place where I think that this is really going to transform things is when we think about disaggregated data. And so already, if you look at kind of recent advances in a lot of fields in economics in recent years, it really hinges on having disaggregated data. So think about the stuff on inequality and opportunity. It's hard to measure inequality with aggregated data, or all the work that's been done in development on misallocation. Again, if you have highly aggregated data, you're not going to be able to measure how things is misallocated across firms, or thinking about political economy on a more disaggregated level at the level of communities. And oftentimes, rich disaggregated data do exist, but unless we're talking about the very modern period, which is what much of the literature has focused on, they tend to be, trapped in hard copy, and manually converting these sources is just way too costly. Maybe some of it's been done for countries like the US, like the US Census, where there's a huge demand for that, but by and large, this disaggregated information is trapped in hard copy, and it's not going to be feasible to type it all in by hand. But these methods really have a potential to transform that. The methods kind of that we need in the compute essentially already exists, but these tools need to be fine-tuned to our applications. That might require some methods innovations, some tailored interfaces, because the interface you interact with is going to be really important. You shouldn't think of deep learning as a technology that in its current state is going to replace you as the human. Think of it as something that can augment your human capital. And for that, you need to have an interface that is intuitive to interact with. And around these things, there needs to be an active research community. And so today I want to just quickly give a few motivating examples. And so I know that some of you may have thought of this, thought about these questions before, but to other people, this may be newer. And I want to give some examples from my recent work of how these methods can be used. And I also want to say, like, why deep learning? Why not other alternatives? And then I'll talk a little bit about the novel resources that we've been working on for implementing deep learning pipelines at scale, in particular an open source Python package that we've developed for doing document image analysis on scans of documents like tables. So yeah, this is what I'm going to focus on. Okay. One case that I've been working on, for the past while is looking at historical newspapers. And we are extracting structured data from historical newspapers at scale. And so once you have structured data, like say headlines, articles, captions, these can be used to measure sentiment. They can be used to query content in a way that accounts for complex vocabulary. You can study how ideas diffused and evolved across time. You can measure polarization and the discussion of various topics. There's just a ton you can do with modern NLP methods, but you need structured data for that. And so we're using deep learning to extract this data from over 35 million page scans that span over 10,000 US newspapers across a period of over a century. And so if you were to take a page scan and just stick it in any commercial kind of OCR engine that you want, typically what will happen is the OCR engine is going to think this is a single column book, and it's just going to read it across from left to right, even though it almost always has multiple columns. It has no way to distinguish what's a headline from an advertisement, from an article, from a caption. And so essentially everything's going to end up all scrambled up. And the quality of the OCR probably along with that is not going to be that great. This is another example. This is a pretty simple layout, but it still gets like really confused and scrambles everything up and has some unstable output at the bottom. And so essentially, if you were to do that, you could look at what keywords appeared in the news, which is good for answering certain questions, but it's not going to be good for doing other things. Like if you want to think about sentiment, or you want to tag topics, just inherently language is complex. There's lots of ways to say the same things. It's hard to capture with keywords. If you want to trace the dissemination of content, which is often abridged or reproduced without bylines through national news markets. Advances in NLP make all these things possible. Like if you have the actual text, but it's not gonna work if you have text that's all scrambled up and really full of like severe OCR errors. And so essentially what we do is to design a deep learning based pipeline where first of all, we recognize the structured text. And so we recognize what's the newspaper header, what's a headline, what's an article. We digitize those and we stitch them together. So articles, may appear across multiple columns. And then we use modern NLP methods. And all these steps are based on deep learning in different ways. And so this is an example of a layout that we recognize. And so the colors are different types of layout regions, and the boxes are the individual layout regions. And so, when we do this across millions and millions of scans, it gives us hundreds of millions of articles, hundreds of millions of image caption pairs. And you can use modern methods and things like classification and retrieval to be able to figure out who's talking about what, where, when, who's getting things and printing them from the same kind of wire service, et cetera. There's just kind of a huge amount you can do with this data once you've been able to extract those structured texts. And it's just, there's a lot of really cool methods in NLP that have really only been developed in the past couple of years that are really, really powerful. A second example is one of historical disaggregated data. And so as I mentioned, if you want to think about things like misallocation or inequality or social mobility, you're going to need disaggregated data, but it's really rare to have that data over long periods. Typically you'd have them, for just pretty recently with some exceptions, but by and large, historical disaggregated data are pretty rare. In many contexts, these data actually exist, but they're trapped in hard copy. And the cost of digitizing them manually would be prohibitive. So in particular, I've had like a long-standing interest in East Asia's spectacular growth performance in the 20th century. But trying to understand this better with aggregate data, like even things like municipal level data, has been unsatisfactory. And in reality, there are incredibly rich firm and individual level data on the Japanese economy that stretch back to the early 20th century. But it would be just completely infeasible to digitize these by hand. It's hundreds of thousands of pages. It's written in an old form of Japanese that most modern Japanese speakers, they can't even recognize the characters. And just in short, in order to be able to process these documents in any systematic way, you really need automated digitization. And so this is an example of a document that we're processing. And so if you want to imagine this like being in English, rotate it 90 degrees. And this is a series of tables that give balance sheet and personnel information for different firms. Okay, so how are we going to go about processing this? First of all, we divide it into columns, and we use deep learning to pre-process it, to get rid of the background noise. And then after that, we have to recognize the individual layout regions. And then we need to OCR it. Which if
one quick question.
Yep.
Can you go back one slide? One more, sorry. So for this step, how did you how did you create the images which are without the dust, essentially?
Yep. So we had so essentially what creates the background noise is the scanning technology, or like being on thin paper also contributes. And so we had a more expensive set of scans that were very high quality, but can only be done for a limited number of columns. And then most of the scans have the text bleed problem. And this uses CycleGAN, which is an unpaired model, so you don't need paired data, but it's essentially a generative model where you're using deep learning and you have multiple networks, and essentially you have a generator network that's trying to turn this kind of dirty image at the top into the clean image at the bottom. And then there's a discriminator network, and you're trying to fool that. And essentially it learns how to remove the background noise. But the great thing about it is you don't need paired data.
Oh, so you didn't actually needed to have matching data between nicely scanned and non. Okay. No,
you know, it's the documents use like similar fonts and stuff, but you don't need paired data for this. And this is a big part of what really makes it very powerful. You need to have, you know, source and target documents, but they don't have to be the same document.
Okay, thank you.
Try to turn one document into looking like the other. And that's going to be really helpful kind of down the road for OCR, because when you have text bleed, it thinks like the text bleed is ones and things in the background and stuff. So that's why we do that. Okay. So then we recognize these different types of content regions, again, using a layout detection model called MaskRCNN that's deep learning based. And then we need to OCR these documents. And, you know, after a lot of work of working with, you know, existing OCR solutions, they're pretty much all really inadequate. And so we needed to design our own OCR engine. But I don't have, you know, kind of the staff to sit there and label multiple examples of every possible character in Japanese, which is what you need to create label data from scratch. So essentially we were able to do something really cool, also using generative models, where we're able to generate the historical font that was used in the book. So if you go to, like, you know, any kind of modern font set from Adobe or Microsoft or, you know, Samsung, whatever, modern fonts are different than historical fonts. They look different. If you just train an OCR engine on modern fonts, it's not going to work on your historical font. But we were able to use a generative model where we trained it on a whole bunch of different fonts, including some labeled characters from our own data. And this does need to be kind of paired data. But we're essentially able to have a model that generates our historical font. So we can type something in a modern font, and the model spits out a font that looks like the historical font that is used in this book. And then on top of that, we have a model that generates documents that look like our documents. And that's very similar to the model that I just explained here. And so we have actual examples of our document, and we have a version, made in Microsoft Word, and it will turn it into something that looks like our documents. And then we train the OCR engine on that. And this is I think one of the most exciting things that we've done, because once you can generate your labeled data, you essentially have an infinite pipeline for generating data. And so you can train deep learning models on huge amounts of data at very kind of low cost to yourself, because you're not sitting there as a human hand annotating the data. You're able to generate it. And so this is how we kind of have been working on designing our own OCR engine. We've also done something similar on Japanese biographical data, and we're able to publish that in a leading computer vision conference. And so there's just, a lot that's interesting here. So that's just a couple examples of what we've used it for. And before I introduce the resources that we've created to try to lower the cost to others of being able to use these technologies, I also want to say why deep learning? Why are we doing this in the first place? And so generally speaking, there are two different approaches to automating data curation. The first approach would be to write down a set of instructions that tells the computer how to process the data by defining a series of rules. The second approach is that you can let the computer learn how to process the data from empirical examples that you give it, labeled empirical examples. It does that through deep learning. And so these are two very different approaches. The rule-based approach would be the traditional approach. You write down a set of rules about how to process things. Like with a table, you would look for connected white space that separates rows and columns. With text, a rule would be like a keyword. You're looking for that particular match or a regex match. Versus and you hard code out how you're going to process the data, versus you give the computer labeled examples of how you want the data processed, and it learns how to do that through deep learning. And rule-based approaches, I think, are easy to understand. Most of us are used to interacting with computers via rule-based approaches. We write down something that we tell Stata to do, and then Stata executes it. They definitely have their place, but we found that they often perform poorly in our context. And that's really because complexity and noise are the enemy of rules. And our documents, our data, are full of complexity and noise. And this is consistent with a massive body of literature in computer science that has found that deep learning tends to significantly outperform rule-based tasks on a massive number of benchmark tasks. That's essentially kind of the deep learning literature from the past decade. And so essentially deep learning allows us to learn a robust mapping between the raw data and our desired output in a way that, if done well, can accurately process new data that the model was not exposed to during training. So you can think of it as a really powerful universal function approximator that has millions of estimated parameters. So you might think, well, how am I going to estimate millions of parameters on the limited amount of labels that I can produce? And really the power of it is that it would be very rare to train a model from scratch because we can build on what the literature has already done, which is a concept called transfer learning. And so when we're recognizing document layouts, we actually started with a backbone to the model that had been trained on natural images. So pictures of dogs and cats and houses, and the model was trained to classify what was in a natural image, like you would have on your iPhone or upload to Facebook. Even though that's very different than our documents, it's a reasonable starting point because there's things about vision, like just being able to detect edges and et cetera, that are constant, whether it's a document or a picture of a cat that you're looking at. And an even better starting point would be, a backbone to the model trained on documents, which I'll come to in a little bit. But this is just to say that with deep learning, you're almost never going to be starting from scratch. There's models out there. I'll talk about resources for knowing what they are, and you would start with that, and that's going to reduce the needs for labeled data. How much it does that is going to depend on how much that context relates to the context that you want to process. And so deep learning kind of underlies everything that I talked about in the examples, whether it's layout analysis and image pre-processing, OCR, predicting reading orders, post-processing to fix OCR errors, natural language processing, just a huge number of tasks that all use these methods. And in fact, they're pretty similar. So a question I commonly get from people is like, isn't there an app that does this? I think anybody in the audience who's ever worked with historical data understands that the answer to that question is no. Unfortunately, you know, typically off-the-shelf solutions like going and using Amazon Textract or Google Cloud Vision, Google Tesseract, you know, OCR engines are not going to get you close to acceptable accuracy. In particular, the commercial OCR softwares and other off-the-shelf models that are out there are incapable of auto-detecting the complex layouts that tend to characterize most quantitative historical documents that we as economists would want to process. Commercial OCR softwares were primarily trained on clean, modern documents that have simple layouts, like single-column books. Whereas we are primarily interested in noisy historical documents, many of which have very complex layouts. And essentially we're a long ways, you know, technology-wise from achieving artificial general intelligence, which means if softwares haven't been trained on documents that look quite a lot like the documents you wish to process, they're not going to, you know, in general perform in a satisfactory way. And so again, this is an example I showed you. This doesn't look like that complex of a layout, but Google Cloud Vision, the leading commercial OCR solution, gets very confused because this doesn't look like the single column modern documents that it was overwhelmingly trained on. If you can't detect layouts, OCR quality is going to decline as well. Oftentimes the document can't figure out where it should be detecting characters. If it wasn't trained on fonts that look similar, it will get the characters wrong. And the data to train an OCR engine that would work in general on any sort of social science document does not exist. You know, and creating such data would not be commercially lucrative. You know, how big is the market to, you know, process that particular 19th century document that you need for the paper that you're working on. Of course, creating computable measures goes beyond just recognizing layouts in OCR. You need to extract structured information from the documents that you want to process. And again, it's hard to imagine that Google or Amazon is going to have a technology that would allow you to do that in a general purpose way. You know, this is, I've been focusing on tables, but off-the-shelf natural language processing usually doesn't work great either. You usually need to, again, be able to fine-tune the model to your particular context. And since there's essentially a near infinite diversity in the types of documents and text that we as social scientists want to process, I don't think, you know, you're not going to see a technology where you hit a single button and out pops your structured data that you're ready to import into Stata anytime in the near future. OCR will continue to improve, but we need other solutions as social scientists. Another question I get is why not just send data off, you know, to Cambodia or wherever for manual entry? They promise 99.5% accuracy. You know, I've sent plenty of data off for manual entry and probably entered even more data myself, and ultimately have found the experience unsatisfactory. You know, I won't go into all the details, but first of all, to actually get 99.5% accuracy, even with double entry, is something that I think is like very rare. And then you'll spend a lot of time fixing mistakes. And essentially, if I'm going to be spending a lot of time doing something, like let's make it at least be interesting and not just fixing messed up data entry. And also just from a scale perspective, it gets expensive pretty quickly. The good freelancers are busy pretty quickly. So there's just really a limited scale. It's plenty for some questions, but there's other questions we'd like to answer where you just can't do it with what you can afford to manually digitize.
So when you create your training sets, though, because you'll need to provide at some point both the truth and then the examples, do you then get to send all of that out for manual data entry? Is that something where you can sort of tie the two together? And if yes, do you have a sense of like how large a training sample we need to put together in order to be able to do this? Like what the rules of thumb are for thinking about how much we need to put into that?
Yeah, so it's very much going to depend like on your context and what you want to do and how much heterogeneity there is in your data, how close it is to other examples. I think there's kind of two approaches. So you may need to manually create your annotated data. We're also prohibited from like using Odesk and stuff. They don't like that. If I need to do that, I need to find an undergraduate research assistant or somebody who can do manual annotation. And so, in some contexts that might just be too costly or time consuming. And so, one thing that I'm going to talk about this more when I get to our resources. So there's a couple of solutions to that. So first of all is active learning, which helps you to choose more useful examples to annotate so that you can reach your annotation requirements with a lower budget. And so that's something that we very much have focused on to make the annotation less costly. And that's going to make a big difference. A second thing is, as I mentioned with the OCR, the potential to actually generate labeled data. And that itself took some hand-created labels to train, but essentially if we can generate our historical fonts and generate layouts that look like our documents, then we have kind of like an infinite capacity to generate labeled data. And so I think when labeling, yes, it's true that these are mostly supervised methods, which means you're going to need annotated data. And so I tell people, don't think deep learning means you're never going to have to do anything tedious again in your life. When I teach my students, you're going to have to sit there and label your data, potentially. But also you can spend some time thinking about an active learning based approach to choose better samples to annotate or a way to generate data. Maybe it's not perfect, but maybe you can take a really large generated sample and pre-train the model on that and then fine tune it on your much smaller hand annotated sample and lower your hand annotation requirements a lot that way. And so I think that there's ways, if you invest in understanding the underlying methods, that you can actually really reduce annotation requirements. But that's a great question because that's really key to this entire endeavor. Okay. And then I'll just say, some people say, don't the digital humanities do this? Our documents tend to be different than theirs. Our downstream tasks are different. They have their own set of challenges. We're not too likely to have to digitize something from the 5th century, except maybe some people do that. But, on the other hand, OCR errors, layout analysis errors can be really catastrophic. For us, this is something I have to deal with and working with computer scientists. They might think 70% accuracy is pretty good. When that's my data and you miss OCR to 1 at the beginning of the number, now everything is off by an order of magnitude, right? And so really we need oftentimes really, really high accuracy because errors can be pretty catastrophic. Okay. And so that's, essentially the introduction to why we may need deep learning and why there aren't other obvious solutions out there. But at least for me, it took me a really long time to figure out what in this kind of very vast and fast moving literature was relevant. It would be typical for a computer scientist to write like 30, 40 papers a year. They all tend to be pretty short. Like the size of this literature is just like overwhelming compared to economics. And then besides understanding the concepts, you need to understand how to go to your computer and implement all of them. And so we've been working on creating resources that make it kind of easier for people, hopefully, to know where to start. So in particular, we focused on two things. So a knowledge base that has links to useful references, and an open source package for document image analysis. And you can find more about both of these on my website. And so if you go to my Harvard website, which is what probably comes up on Google, then click personal website, because Harvard really limits what I can put on my website. But if you click through the link to my personal website, you'll find the knowledge base, and you'll find links to the software package there. And so the knowledge base is meant for people who either don't have familiarity with deep learning or just have never applied it to kind of economic data before. It's based on a PhD course that I taught on using deep learning to process social science data. So it goes through, essentially what we talked about: why deep learning, what are the rule-based approaches, intro references for an introduction to deep learning. If you don't even know what deep learning is, that's fine. Just go to the Intro to Deep Learning page, and it will give references for getting started. And then, general information about how do you train neural networks. And then we talk about a bunch of methods in computer vision that are useful for document processing, but they would also be applicable to things like video processing or processing photographs, satellite data, essentially any type of image data. Including, like things like I just mentioned, like how you use active learning and other labeling hacks to reduce your annotation costs, to make it possible to create enough labeled examples that you can train a high quality model without having to do an infeasible amount of labeling. It also talks about OCR, whether, what is it, what's under the hood with OCR, how do you use it in practice? And then there's also a bunch of resources on natural language processing, including kind of very up-to-date based topics. And so that's the knowledge base. I'll try to, the literature moves really fast, but I'll try to keep it pretty up to date. There's links to a ton of different resources, and there's actually a lot of great resources that are out there. And so hopefully, if you're interested in this, but not super familiar or haven't used it in these contexts, it will kind of be useful in pointing to the references that we've found super helpful in figuring things out. Okay, so the second thing we've done is to develop an open source package called LayoutParser. And so essentially I worked with a pre-doc, Zizing Sen, and some other collaborators to integrate the models and tools that we developed into an open source package that's called LayoutParser. And the aim is to make it much more straightforward for social science researchers or other researchers to use deep learning and to process document images. And so it provides an intuitive interface for applying and customizing deep learning models for layout detection, character recognition, and other document processing tasks. We'll also eventually incorporate a community platform that's currently under development for sharing pre-trained models as well as full digitization pipelines. And there's a paper where we describe the package, also called LayoutParser, that you can find on my website. And so our motivation is that if you were to go and implement a pipeline for document image analysis from scratch, that would require, a fair amount programming expertise. Currently, there is no full-fledged infrastructure for easily curating document image data sets, or for fine-tuning or retraining the layout analysis models that allow you to recognize the structures in the documents. So like, the headlines, the articles, etc. If it's a newspaper, different types of information in a table, etc. It's also difficult for research teams to learn about how full pipelines are implemented. And this, will lead to people reinventing the wheel where it's not really necessary or socially efficient. And so this package has different components. First of all, it has an off-the-shelf toolkit for applying deep learning models for layout detection, character recognition, and other tasks. You can just use it straight off the shelf. All you need is 4 lines of Python code, so you don't really need to know much of anything. This will work if your documents look a lot like the models that we've pre-trained, which probably they don't look similar enough for it to be an acceptable level of accuracy, unless you want to process documents that really, really look like the models we have. Those pre-trained models there are also going to be very useful if you need to train your own customized model, because you can use them as a starting point. And remember, the better your starting point, the less data that you yourself will need to annotate. But you'll still need to annotate some data. Document layout analysis, so recognizing the different content regions of a document is a supervised task. That means that in order for the computer to learn how to do it on your documents, you'll need to give it labeled examples from your documents. And this package comes with tools to make data annotation more efficient. It also comes with an interface for being able to fine-tune your own layout analysis model, potentially using one of those pre-trained models as a starting point. And then finally, the community hub. And it's implemented with simple Python APIs. And so this is kind of a flow chart of how it works. You will feed it an image of a document. You could potentially just use the models off the shelf to detect the layout structures in the document. So what are the individual headers and columns and cell values, or different types of regions of a table, etc. Or, your documents may be different from the documents that we have pre-trained models for. And so you'll need to do some efficient data annotation using the tools that this provides, and some customized model training. But that will also give you the document structures. Then you can OCR those. And finally, there's also tools for being able to store that data in a way that's efficient and visualize the output. Okay, and so it's built upon Detectron 2, which is an object detection framework produced by Facebook AI Research. And if you want to use, as I mentioned, one of the pre-trained models we have, this is all the code you need. Just those 4 lines of code, that's it. And it will run on your documents. These are currently the models that we have in our pre-trained models zoo. Some of them trained by us, some of them trained by others. Newspaper Navigator is trained by Ben Lee, who was like a computer scientist who worked with old historical newspapers from Library of Congress. So these are the pre-trained models that are there, and we'll continue to add more models. And we hope that people who use this package, which we've had a lot of interest, will also be willing to contribute their models. And so this will give you, you run the model and it will give you different types of layout data structure. So it will tell you essentially the coordinates of your region. And so oftentimes that may be a rectangle. Imagine the picture of the newspapers I showed you, and there's a rectangle around each headline and each image and each caption and advertisement, etc. If your documents are skewed when you scan them, the output may be a quadrilateral. So you have, those coordinates. And text blocks consist of the coordinate information and also extra features like the text itself from the block, the reading orders. And you can even potentially combine these in a hierarchical way, which may be useful for some types of documents. There's a wide collection of transformations like shifting, padding, and scaling, or operations like intersect and union that are supported, which may be useful because once you have these layout regions, you may need to work with them in multiple ways. Like you may want to pad them before you send it to OCR, so you add a little bit of extra space in case the model has chopped off the edge of one of the characters, for example. LayoutParser has a series of wrappers to call existing OCR engines. So the main ones are Tesseract, which is open source, meaning it's free, and Google Cloud Vision. It also comes with a deep learning based model that you can take and potentially modify that code to your own context. And hopefully this is something that will be updating in the future. It's a very narrow model, but you can use that model to kind of see how you would code up your own OCR. And this is, again, like I said, like we've been doing a ton with OCR. And so hopefully we can get some resources and make more of our OCR tools like available in a user-friendly way. It supports exporting layout data into different formats like JSON, which is probably the most flexible and common one to work with, or CSV. And it also supports loading data sets in layout specific formats. So if you already have annotations that you've created somewhere else, you can just load them into this tool. And it's built with an integrated API for displaying layout information along with the original document. And so this is what that looks like. So this is just a paper, a page from the PDF of the LayoutParser paper. And we ran our pre-trained model on it, and you see, it recognizes the section headers and the text and draws boxes around them, and you can visualize what those boxes look like, or you can visualize the OCR text itself in the place on the page where that particular word appears. And so these are useful for checking the integrity of your output. Okay. And so as I mentioned, there's some models you can use off the shelf, but our documents are incredibly diverse. You probably want to process documents that look nothing like the documents that I've processed or that people who've used this and contributed their models have processed. And the biggest challenge to you of doing that is making the annotation feasible. You don't want to spend an infinite amount of your time or your RA's time just labeling boxes, for hours on end. And so how do we get around that? This comes back to the previous question. Essentially, one of the main ways, if you're not able to actually generate your data or find some data set that somebody else has used, you need to create your own annotations. You want to find a way to choose the most useful examples to annotate, which is typically not going to be drawing them at random. And that comes into an area of deep learning known as active learning, which is really not about the computer replacing you, but you interacting with the computer to make the pipeline as efficient as possible. And so in deep learning, active learning methods typically select samples to annotate at the image level, which we found was actually pretty inefficient for documents, because on a given image, you may have some very common objects and your model has already learned how to recognize those. You don't need to annotate those from scratch. But you also may have more unusual objects on that image, and those are the ones that you do need to annotate. So we worked, so I'll just kind of show that with this distribution, right? Imagine this is the distribution of different layout regions, and in the middle you have some very common types of text regions that are very overrepresented in your data that you need to recognize. And then in the tails, you have these more unusual text regions, right? And if you've worked much with historical documents, this probably rings a bell. And if you just draw them at random, you're going to have way too many samples from the center of that distribution, you're going to end up wasting your time or your research assistant's time labeling things you don't need to label because the model's already figured it out. And you're going to be underrepresented from the tail. So you're still not going to do good on those more unusual regions. And so we'd like to, sample, oversample from the tails. But the problem is the layout distribution isn't observed ex ante. You haven't looked at your documents yet. So how are we going to solve this problem? What we did was to develop a framework called Object Level Active Learning, or OLALA, that's designed specifically for documents. And in this framework, only regions with the most ambiguous object predictions within an image are selected for annotators to label. And this optimizes the use of the annotation budget. And so essentially there's an object level scoring function. I'm not going to show you the details of it because then I have to explain how the object detection works and we don't have time for that. But essentially the scoring function evaluates prediction ambiguity and uses that ambiguity to determine which objects should be selected for labeling. And we essentially use a perturbation-based scoring method based on both the bounding box and category predictions to account for how uncertain that, to estimate how uncertain that prediction is going to be. So we hypothesize, if when we perturb things a little bit, it leads to a very different set of predictions, then your model is probably unstable and you need more annotations for that particular type of objects. And essentially we have a paper, we do lots of simulations to show that this works pretty well under certain circumstances. In practice, if you want to do this, you need a software interface to do this, right? So we work to integrate what you need to implement this into an open source software called Label Studio. And we also made some other modifications to it to make it more efficient for documents. And this comes with the LayoutParser package. And so this is an example of how you use it in practice. And so let's say you have a preliminary model. You run it in panel A, and you can see there's some problems. It fails to detect that headline. Some of the boxes are kind of off. If you want, you can predict the predictions that are most ambiguous and try to focus your attention on those. You can also show everything as opaque, which helps you to easily spot places where it failed to draw a box altogether. And essentially there's tools like that within this that allows you to efficiently correct the model predictions rather than starting from scratch. And this is going to really lower the amount of time you have to spend doing a very tedious task, which is sitting there drawing boxes on your document. And as I said, this is, the original Label Studio package was super buggy. It's a mess to implement. You're messing around with port numbers on, AWS forever. We've worked to make it more efficient, and we're going to kind of keep working to improve that and keep working to kind of update the package. Once you have those annotations, LayoutParser makes it easy with some minimal Python code to fine-tune your own layout analysis model using the labels you created and potentially using one of our benchmark models or using some other model that you upload as a starting point. And for example, we're able to use these tools to do this pretty complex layout recognition on these Japanese documents. There's other things you can do with it, like rearranging text to achieve better OCR. And yeah, this is just to say that, it works on, practical examples of complex documents that are used by researchers. And so just, in conclusion, I've argued that deep learning offers enormous potential to unlock novel sources of data, whether it be from text or from images. And becoming familiar with these methods, how they apply to economists, how they can be implemented and debugged is incredibly valuable. But it also involves a lot of startup costs because there's just this vast literature, and the vast majority of it was written not with social science in mind at all. And so our hope is that by having a knowledge base that points people to some useful resources, and then having this open source document image analysis, which, you know, we'll work to continue to update. We hope other users will do the same and kind of get involved with the package. We hope to make it easier for researchers to study questions that they find interesting, that they find meaningful, you know, without having to have quite such high barriers to entry. Okay, so that's all I have. Are there any final questions?
Yeah, thank you so much, Melissa. That was amazing. Thank you so much. Do we have questions from the floor? I wanted to follow up, if I may, on what Leslie asked earlier on, the trade-off, sending stuff off for digitization versus training models. I have on occasion tried to endeavor what you do now, but always found that for the things I was interested in, I might have, say, 500 counties and a few dozen variables I'm interested in that have a certain layout. And for me, the trade-off always worked out. It's easier to get it digitized because the next set of tables I might be interested in looks completely different. So I again invest weeks to train a model. And in the meantime, I have the data ready to use. So would you say that what you are now working on makes sense, especially if one has literally millions of pages as opposed to just a few hundred? Or where would you say is the threshold where a researcher just shouldn't evade working on OCR and deep learning and all that?
Yeah, so I think it's going to depend. Obviously, like the smaller the scale of your data set, the cheaper that manual digitization is. And so essentially, like manual digitization has more or less like a fix, like a variable cost per unit, right? Whereas you can think of, you know, these deep learning based approaches as you pay a fixed cost up front, which could be very large, you know, depending on what you're doing and what the resources are and how similar it is. But then your kind of marginal cost is close to zero. It's not exactly zero. You know, like I mentioned for this newspaper thing, we're running 1,000 virtual CPUs on Azure. Fortunately, we got Microsoft to give them to us because they have like excess capacity, but there's some cost to compute and there's some marginal cost, but it's very minimal, you know, compared, it would be like a small fraction of a cent for each additional page you want to process. And so I think that part of our goal is to try to reduce those fixed costs. And the more we can get kind of people to participate in this, obviously, like the lower they will be, because the more people will, you know, use it and then upload their model, the more likely that you can just go try one of those models. And with those 4 lines of Python code, that fixed cost would actually be less than, you know, sending off your small data set. But right now it's such a new technology that those fixed costs are probably going to be higher because, again, your document is probably going to look different than the other things that have been processed. So I think that we're kind of at a point where it's hard to say what the precise boundary is because, you know, how much work, what the fixed cost is going to depend on kind of what your document looks like. But I think that as more and more people kind of use this, then the fixed costs come down because hopefully people contribute to the package, the interface gets better, there's more pre-trained models that will just kind of work for you. But yeah, I'd say that right now it's at a stage where if you have a data set that's pretty feasible for manual entry, that's probably the easiest approach. Although, you know, maybe not 100%. Like, I mean, I mentioned I taught a class on this and, you know, some of the students wanted to do really weird stuff and some of them wanted to do kind of more standard looking stuff. And for some of the more standard looking stuff, it actually does, like the pre-trained models do a lot better than Google Tesseract and, you know, got them to, you know, it's hard to say, it's not my data. I didn't look at every row and see exactly how good it was, but it seemed to get them to a more reasonable place.
Is there a network of pre-trained RAs or postdocs who are really familiar with doing this, who are looking for collaborations? Is there an easy way to identify people who have expertise in this so that you don't have to relearn it all from scratch if this is not your main focus of expertise?
Not really. I think it's actually like you're almost best off like taking a smart economics student and training them, because when you think about like what we might possibly pay compared to like Amazon or something, and there's a huge shortage and there's a huge number of people who say they know deep learning, but they don't like, because it's like that's kind of my experience. Like a smart undergrad who's interested in economics can figure this stuff out. And I think that if you look at like what we might possibly pay and you try to get somebody who says they have expertise in deep learning, it's your odds are you might not be very satisfied with the quality of that person.
Thank you, Melissa. We have 3 more questions in the pipeline. Simon, Klaus, and Kailing.
Thanks, Sasha. Thank you, Melissa. Just on that point, I'm with Klaus and Paul and Nathan, one of the co-founders at Soda here. And just to that question before from Leslie, you make a good point. However, what we've found is that we have an ecosystem of students and pre-doc, postdocs. They're driven by the why. So often they come across from computer science because they're really looking for interesting applications. And so I have a student at the moment who's taken a year out from their PhD to work on interesting NLP, because they don't tend to get that kind of exposure in the comp sci area. And then he'll go back, finish his PhD. It's in some very elaborate, neural network task, but he's really enjoying and seeing, the value. So I think if you can sell the why, then I think there is that opportunity to get the crossover from that really good talent. My question was actually more about just from zooming out a little bit, we also do some synthetic or generating synthetic label data. We use a little bit of GPT-3 to do some of that and exploring its opportunities. What we're really doing is we're moving the task of the human from what used to be heavy labeling. We find now actually we're calling in the human more for validation. Because we need to understand, once we build some elaborate system with perhaps synthetic data, we then need to say at the end of the day, does it actually make sense? Can we sort of send it to the editor and say, we actually think we've got right to the end of the pipeline, it's still telling us something that's useful. Maybe could you say something about that and how you see, is the next frontier we do automated validation as well? I'm not sure if you've thought about that problem, what we look forward to in that area.
Yeah, no, I think that that's definitely true, which again comes down to maybe having an efficient interface, as I'm sure you found, to be able to do that and see if it makes sense. So I think this is kind of very related to what I mentioned that we've been working on currently, which is being able to actually train an OCR engine on a bunch of data that we simulated ourselves. And then obviously you need to go and look at it and make sure, and actually, you still need some labeled data to validate that it's correct. And you might actually want to think about things like active learning in that context, because if you're just drawing your samples at random, maybe you're not picking up on the less common errors, but they could still be outliers that affect, your analysis or whatever. So I think that, whether you're kind of labeling or validating, it's kind of a similar set of concerns of needing to have an efficient interface for the user and needing to be able to sample correctly, which I think is, as economists, is something that we think about a lot and actually kind of have an advantage to thinking about maybe over some more purely kind of technical types. So I think that that's definitely relevant.
Klaus.
Yes. So one question regarding, so let's say we have now a million documents, and we now manage to digitize all of them. Something that you have done in your research. So would there a way now, for example, for you to figure out what type of sampling strategy we should have used in the beginning to get the same empirical results? Because if we do population census, yeah, we get everybody, but we also know how to take samples of the population to get representative samples of the target research question in mind. So maybe one possible avenue of this type of research is what's actually the optimal sampling strategy for historic documents to get representative samples, because then you don't have to digitize a million documents.
Yeah, I think that that's a super fascinating question. I mean, it's probably going to be domain specific, right? So you have this huge literature on networks where people talk about how any sample is inherently biased and you need a census. And but obviously that isn't the case with lots of types of questions. So yeah, I agree that that's like a super fascinating avenue.
Kaling?
Okay, very interesting work. I can see you put a lot of efforts here. So Melissa, can I just when I see you use the Japanese documents, I'm thinking the language itself is moving. So the language that used 50 years ago, 100 years ago in Japan could be different from today. So there also, it's the newspaper language or whatever language could be different from other contexts. So I'm thinking maybe you have thought about it because you have worked on this. So after you have digitized all this, there's still, I can see many works to be able to extract the meaning underlying the language. Have you just want to pick up on that?
Yeah, so I think that in the case of the Japanese documents, a central thing that we're really interested in getting out of them is names for tracking people across time and across firms and networks of connections and stuff. And there, the main challenge is just there's lots of characters that aren't in use today. And that's why there's not a commercial OCR engine that will work and why we had to kind of go into thinking about our own font. I think if you wanted to analyze Japanese newspapers, which someone might want to do, then you're into a realm of kind of other potential differences in language and grammar. And I'm not an expert on the historical Japanese language, but I'm sure that comes into play. In the context of our newspapers, which are from the United States, I'd say English itself has not changed a tremendous amount across the 20th century. But the reason why you might think an off-the-shelf language model might not perform as well as you'd like is because our data has OCR errors in it, right? So you can kind of try to make it as clean as possible, but pretty much the vast majority of off-the-shelf language models have been trained on pretty clean data that doesn't have OCR errors. So we've been working a little bit with some computer scientists at Stanford to try to actually pre-train a language model on our corpus, which is something that we're really well poised to do, because pre-training a language model takes a massive amount of data. But we have hundreds of millions of articles. So we literally have a massive amount of data, and pre-training a language model is unsupervised. So that's actually a task where what we've been talking about label data, it doesn't come into play. The challenge there is it takes far more compute than I'd ever have access to, but these computer scientists at Stanford have access to an extremely large amount of compute. So I think that will be part of what we do, and kind of very much speaks to this question that maybe our language models that are pre-trained on Wikipedia are not going to do so well on this historical stuff. I mean, I think they actually do fine, but I think that you can get better performance actually, potentially pre-training. And we'll have to see how necessary it is, or if we just, used 120 GPUs to do something that was marginal. But that's that's one thing that we're working on moving forward.
Thank you so much, Melissa. So we are now a few minutes over time, and it's already late at the East Coast. It's after 8 p.m., I assume. So thank you so much again for taking the time to talk to us and present your work. And we hope to one day welcome you in person in Melbourne. And in the meantime, all the best, Melissa. And I'll have a chat with you in a few minutes. I sent you a link, and then we pick up from there. Thank you. Bye-bye.